Thanks, Nikhil. So I'm going to talk about online auctions and multi-scale learning, which is a joint work with Sebastien, Bubeck, and Nikhil Devanur from Microsoft Research, and Zhiyi Huang from Hong Kong University. OK. You might have seen applications of dynamic or online pricing in different corners of electronic commerce. And I don't know why I'm saying this to this audience. You might also have seen different applications of online pricing in your life. For example, airlines and flight ticket prices that change over time, and electronic retailers and the price of the items that sometimes change in a span of 1 month, 2 months, or years. And there are also emerging applications, potential applications for online pricing, things like cloud service prices and reserve prices for ad auction. And in all of these examples, there is a monopoly seller that has a service to provide or an item to sell. And the objective is to tune the price over time to maximize the revenue of the monopolies. Why the monopolies are using pricing? Pricing are simple, easy to optimize, and natural. And still, we don't know, are they good in terms of maximizing revenue for a dynamic setting? And we are trying to address this question by saying that how we can tune the prices over time in order to get good revenue for the monopolist. Let me formalize this problem. In the full information setting, we have a monopoly seller that has a single item with unlimited supply. And we have buyers that have values for this item. And they are myopic in the sense that they are following a take it or leave it approach. Now, we have a game. At each time t from 1 to capital T, the seller posts a price P of t. And an adversarial buyer with value V of t comes, submits his value to the platform, and takes the price if the value is greater than the price, takes the item if the value is greater than the price, pays the price, and otherwise leaves it. And we go to the next round, another buyer, and if the values are smaller than the price, there will be no trade. So we are in a full information setting in the sense that the buyers submit their values to the platform. We can also think of the bandit information version of this problem, in which the seller posts a price. The buyer has a value for the item. It doesn't submit the value. And the trade happens if the value is greater than the price. So the difference in this game is that the only bit of information that the platform realizes after interacting with the buyer is whether trade happened or not. OK? So for both of these settings, I define the revenue of a pricing algorithm to be the total revenue that the algorithm generates over time. At each time t, the revenue is going to be equal to the price it posts, P of t, if the value is greater than the price, otherwise 0. I denote this quantity by g of alg. For the benchmark, I'm looking at the maximum revenue you can get by posting one fixed price at all times. I denote this benchmark by optimal price, g of max. And I'm also looking at a variant of this benchmark, which is called delta-guarded optimal price, which indeed is the maximum revenue you can get by posting a price P. But among the prices with market share, which is the fraction of times that they get sold, more than delta. I denote this quantity by g max of delta. And the performance measure in this talk for online pricing algorithm is something that we call convergence rate. Let me define what convergence rate is. A convergence rate of an online pricing algorithm is the minimum number of rounds required so that the revenue you get from the algorithm is at least 1 minus epsilon times the optimal revenue in hindsight. OK? You can define the same thing for delta-guarded benchmark. And informally, the question we are answering in this talk is the following. How can you design an online pricing algorithm that achieves a tight convergence rate? So I have to define to you what's the meaning of tight in this setting. And with that, I'm going to switch gears to another problem, which is kind of maybe familiar for at least one person in this audience, maybe 2, or maybe 3. So this problem is sample complexity of auctions. This is the following problem for single item auctions. Suppose you have an underlying distribution D which is unknown, and then you have M samples run IID from distribution, denoted by V1 to Vm. Now, you aim to find a price, P of alg, given the samples you have, so that if you post that price to a fresh sample from a distribution, the expected revenue you get is at least 1 minus epsilon times the maximum revenue you can get from this distribution. And now the sample complexity problem is asking the following question. What is the minimum number of samples required to have such a guarantee? This problem has been studied during past couple of years very heavily, and we understand upper bounds and information theoretic lower bounds for this problem in different settings under different distributional assumptions. Okay, so how it is related to my convergence rate problem? In fact, my claim is whatever sample complexity result you get for the single item auction is going to give you a lower bound for the convergence rate problem in the following sense. So suppose you give me your samples. Now, I'm trying to use an online pricing algorithm to create a sample complexity algorithm, and this will imply the lower bound. Here's what I do. I run my pricing algorithm on these samples in any arbitrary order to come up with prices P1 through Pm. And then I pick one of them uniformly at random, denoted by P of alg in this slide, and then I post that price. Now, it's not that hard to see if the number of samples that you have is greater or equal than the convergence rate, then the expected revenue you can get from this randomized price, which not that hard to see, is basically the average accumulated revenue of the online pricing algorithm, is going to be at least 1 minus epsilon times the maximum revenue you get from this distribution. So this implies that sample complexity is a legit lower bound for the convergence rate problem. And we know information theoretic lower bounds here. Now I can ask the formal question I'm addressing in this talk, which is the following question. Can online pricing algorithms for the adversarial online case achieve convergence rates that are matching the known sample complexity lower bounds? So this is a more general setting because, as I said, this is online and adversarial, so it might be unexpected. But the answer is surprisingly yes. And here are our results. So the rows are for full information, bandit information online pricing with respect to unguarded and guarded benchmarks. And the last column is the convergence rates that we get. And the first column is sample complexity or other information theoretic lower bounds known for this problem. So as you will see, so one nice thing when you're computing with respect to the unguarded benchmark is, in fact, that the convergence rate that we get is scaled linearly with the optimal price P star rather than the maximum range of the values, which is H in this table. And also, if you think about the full information, we match the sample complexity lower bound. And when you think about the delta guarded benchmark, the result is even more interesting because we actually get the first polynomial convergence rate for this problem. And for the full information, we match the sample complexity lower bound. And for the bandit information, there exists no information theoretic lower bound. So what are the significance of these results? First of all, they're generalizing the sample complexity to an online adversarial setting. And second, they are tight in the sense that they match the information theoretic lower bounds of sample complexity in some cases, and they are pretty close to the known lower bound in other cases, and there are some remaining cases that we haven't yet solved. And also, this is the reason I actually like this result, is that if you think about the convergence rate, they scale linearly with the optimal price and not the maximum range. So for example, if you're in a scenario that you have a tight you have a loose upper bound on the range of the values, then you are not going to lose a lot of regret, or let's say get a bad convergence rate. And these results can be generalized to the case of learning Myersonian-like auctions, which I'm not going to talk about in this talk. We have results in the paper. OK, so what is the general idea of getting an upper bound here? This is indeed a well-studied problem, and people have thought about this problem as an online learning problem. And they try to use online learning algorithms in a black box fashion. So this is indeed what happened in the papers Blum et al. 2004 and Blum and Hartline 2005. The idea is pretty simple. You assign one arm or action to each of the prices, and then you can define the reward of a price P. This green line is a price P. Is a value at time t v of t, and these are the prices. So you can define the reward of some particular price to be equal to the price itself if it is smaller than the value, and 0 otherwise. OK, so if you use the online learning algorithm in a black box fashion, you can get online pricing algorithm in the full information setting from adversarial expert algorithms, and you can get online pricing algorithms for the bandit setting from multi-arm bandit algorithms. However, here is one nice observation. If you use known online learning algorithms in the literature in a black box fashion, then this is what you get. The regret is going to scale linearly with maximum range, which is some known fact in online learning. And what is regret? This is basically what your benchmark gets minus what your algorithm gets. However, in this particular problem, we have different arms, and the different arms have different ranges. In particular, if you think about some price P, the reward you get from this price is upper bounded by the price itself. It is either 0 or P. Now, here is the question. Can we exploit this reward structure in order to get a better regret bound? And in particular, what we are looking for is that you get a regret bound such that it scales linearly with the range of the arm and not the maximum range. And we call that multi-scale regret bound. And with this brief introduction, I'm going to switch gears to pure learning problem and a framework that we have in this paper called multi-scale online learning. So what is multi-scale online learning? It is, in fact, the standard setting of learning from experts or bandits in which I have a finite set of actions denoted by A. And then each action or arm has a different range. In particular, action I is in the range 0 to Ci. OK, so here is a game in times t from 1 to capital T. At each time, the algorithm picks one of the actions. And simultaneously, the adversary picks a reward function, let's say g of t. And the algorithm gets the corresponding reward of the action it picked. And now we have a full information setting in which the entire reward function will be revealed to the algorithm. And we have the bandit information setting in which the reward of the arm that the algorithm picked will only be revealed. Now we define the reward of the algorithm to be the total reward it accumulates over time, denoted by galg. The reward of some particular action I to be the reward you get if you just play that action at all rounds, denoted by gi. And my benchmark is the maximum reward you can get by playing the same action at all times, denoted by Gmax. And I define the regret with respect to some particular action I to be the expected gi minus galg. OK, so what I'm looking for is something called multi-scale regret bound, which is the following type of bound. For every action, the regret with respect to that action scales with the range of that action. And here are results. So if you think about the full information experts problem and assume that the number of actions is equal to n, then this is what you get from the standard bounds. For every arm, your regret is going to be upper bounded by epsilon gi plus some other function, which is 1 over epsilon log n Cmax. This might be familiar to you if you're familiar with online learning. And this scales linearly with maximum range. With our algorithm, you actually get a regret bound, which is epsilon gi plus some other term, 1 over epsilon log n over epsilon times Ci, which scales linearly with the range of the arm rather than the maximum range. Well, and for the bandit problem, if you use the standard bounds, you get such a regret bound, which is epsilon gi plus 1 over epsilon n log n Cmax. This, again, must be familiar to you. And if you use our bandit algorithm, you get the following regret bound with respect to all arms at the same time, epsilon gi plus 1 over epsilon squared n log n over epsilon Ci, which scales linearly with Ci, but it doesn't have the optimal dependency on epsilon. And in fact, we show that with respect to the optimal arm, which is the arm that gets the maximum reward, you can actually get a multi-scale regret bound that has the optimal dependency on epsilon also. OK, so let me translate these bounds in some form that might be more familiar to you, which I call them the pure additive regret bounds. The rows are the expert problem and the bandit problem. And the first column is the classic bound that you get from the, let's say, multiplicative weight update and x3. And then this column is the result that we get. So you see, we get the same dependency on t and other parameters up to logarithmic factors. But our bounds are multi-scale in the sense that I defined earlier. Now, I need to show you how we can prove the convergence bounds that I promised by using this new learning framework, which is easy. And second, I have to show you how to get these bounds, which I'm not going to prove to you what my algorithm does, how my algorithm gets these bounds. But I try to show you the essence of the ideas behind the construction of this algorithm. So here's my algorithm for the full information setting. What we use is a family of online learning algorithms that is called online mirror descent. So you can think of online mirror descent as a parameterized learning family that each member is using some convex function called Legendre function as the base. And then based on that function, it does some update rule and some projection, and in this way learns the distribution over the set of actions. Okay, so the particular Legendre function or convex function that we use for our algorithm is weighted negative entropy, which is the following function. It is basically minus entropy, but you scale each term separately with the range of the arm. Just some interesting thing, if you remove these CIs and you use negative entropy, then online mirror descent will actually give you multiplicative weight update, which is the well-known algorithm that we all know for the expert problem. Now, what does happen if you have this modification? Suppose that each time the algorithm picks one of the actions with a distribution called PT, and I'm going to show you how this algorithm, which I call it multi-scale multiplicative weight update, is going to update PT at each iteration. Here is the gradient update. Oh, so let me actually read it to you. So it is basically like multiplicative weight update. You multiply PT for each arm by e to the power eta GIT divided by CI, but we have this factor CI. So you're normalizing the reward of the arm I with the range of that arm, and then you update. This one is not that different from multiplicative weight. You just have these CIs. The projection is more interesting. So here is how you project to the simplex. You multiply each weight that you got from the gradient step update by this function, e to the power minus lambda over CI. And you pick lambda such that these numbers sum up to 1. And after you found these numbers, you just normalize accordingly. I call this projection step because of the fact that we are using online mirror descent, Bregman projection. And these are defining the update rule of my algorithm. Besides this, I'm actually using a different initial distribution than the one that you use for example, multiplicative weight update. This is the right initial distribution for this problem. It is basically putting all the mass on the arm that has the minimum range and mixes that with the uniform distribution. And then with these three, you can get the multi-scale regret bound. For the bandit information, we are using the bandit version of online mirror descent called the stochastic online mirror descent. That I'm not going to go through the details of that. Oh, by the way, the intuition that why we are using this initial arm, this initial distribution is that we try to explore the small range arms at the beginning and then move to the bigger ranges later. And this is going to help us with that. So let me summarize my talk in the following way. So we looked at online pricing. And we showed how this problem is basically an instance of multi-scale learning. We showed how to do multi-scale online learning with a variant of online mirror descent. And this improves the past literature in the sense that it achieves tight sample complexity bounds for the online pricing, even though we are in an online adversarial sense and there is no underlying distribution. This also extends naturally to Meyerson-like auctions. We have some cool bounds for that. See the paper, please. And I would be happy to talk about it offline. So the drawback, if you think about the Meyerson-like auctions, is that by doing the multiplicative weight update or multi-scale multiplicative weight update, this is not be computation efficient because you have exponentially many arms. And now this is one interesting open question. Can you combine this with the recent advances on Oracle efficient learning and get efficient algorithm? So with that, I conclude my talk. Thanks for your attention.